Hello and welcome back to Power Electronics with Dr. K. And in this video, I'm going to show you how to model silicon carbide MOSFETs and silicon carbide Schottky diodes in LTspice. We're going to utilize the Cree library for this example. If you like the channel, please subscribe and hit the bell for further notifications. Here's an overview of the video. First, we'll demonstrate how to use the Cree Wolfspeed new silicon carbide SPICE models in LTspice. And I'll provide links to the Cree website where you can find these models in the description below. We'll discuss the Kelvin terminal on the 4-pin package for the silicon carbide device. Many of the high power packages are coming with Kelvin terminals on there for the gate to source connections. Once we've built the model, we'll run a simulation and we'll compare those simulation results to the datasheet. Before you begin, let's go and get the library files from the Cree/Wolfspeed website. I've selected Cree because they are one of the leaders in the silicon carbide space. And the silicon carbide device space is growing rapidly. We are seeing numerous applications where silicon carbide is the right selection choice for the design. That's due to its extremely low loss, high voltage, and the ability to switch at very high speeds. In addition, we have silicon carbide Schottky diodes, again, low loss and very fast. Here on their Power Products page, and again, I will provide this link in the description, we can see the different models of the discrete silicon carbide MOSFETs. And let's just jump over there. And when you click on this page or on this link, you'll come to a registration page. You'll have to register before downloading the model. Now, I have registered and have already downloaded the model and placed it into a directory. After you've downloaded the file, we can place it in a file folder, and I've placed the archived folder that contains all of the models from Cree in the Documents LTspice folder of mine that has our lib folder in it. So I'm going to extract this, and let's do that quickly here. We'll extract all, and we'll see there's two more folders that are also archived, and I'm going to extract those. And let me go back up here, and let's extract the Schottky diode folder. And there we have the devices. And so now I've extracted those in this folder. I can remove the archive folder, and let me come up and remove that archive folder as well. And notice that we have a folder with the MOSFET silicon carbide models and a folder with the silicon carbide Schottky diodes. So let's just go up to here, and one of the things you'll see, there's a folder called documentation. There is a PDF on how to utilize this, and I encourage you to read that. It'll be in the folder. However, I'm going to go in there, and one of the things I want out of this folder are the LTspice symbols. And so I'll go back up a folder. So they're in a subfolder called LTspice symbols for our silicon carbide MOSFET devices. And I'm going to copy all of these, and I'm going to copy them. And I'm going to go back into the LTspice lib file, so LTspice lib, and there is a subfolder called SYM, and all the symbols are in there. And I'm going to create a new folder in here, and I'm going to call that Wolfspeed. I'll call it Silicon Carbide SiC Wolfspeed devices. And you can call it whatever you want. And this is the folder that I'm going to use to place the symbols for our different devices. So the device I'm going to select today is a TO2 RJ47 package, and it's 4 leads. One of the leads is going to be the Kelvin pin on it, and we'll talk about that in a little bit. So I have our MOSFET devices in there. I'm going to come back up, and the other devices that I want to put in there for symbols are going to be the symbols for our Schottky diodes. So if we go in here, and there's folders for the different ones. The Schottky diode that I have pre-selected for our example today is a C3D series. So I'm going to navigate into that folder, and then we'll see another subfolder for the SPICE models. And notice we have another folder in here that has the symbols that are archived. And so I am going to extract that. And we'll go and see all the Cree diodes. And so what I'm going to do now is I will select all of these. I'm going to copy those, and we'll have all these symbols. And let me navigate back into the symbol file folder that I have just created. And we're back into the LTspice top directory, and here's our symbol folder. So LTspice lib sim, and I just created this Silicon Carbide Wolfspeed devices, and now I'll paste the diode symbols in here. So there's all our different diode symbols as well as our MOSFET symbols down here. So we have our symbols in there. So our next step now is to go into LTspice. Here I have the beginnings of our example circuit that we're going to use for this demonstration, and it's going to be a DC chopper circuit, and I'm going to have to install a low side switch down here below our inductor in series resistance, and I have our gate to source pulse generator, or our gate driver if you will, already set up, and we have a DC bus voltage of 400 volts. And one of the things to note is with a series resistance and inductance, we're going to have a time constant for our transient, and that time constant for a series RL circuit is R divided by L. And so 20 ohms divided by 20 millihenries is going to give us a 1 millisecond time constant. And you'll notice down here at the bottom, I have our transient set up to go to 5 time constants or 5 milliseconds. We're going to be switching at a relatively fast rate. I have a switching frequency of 20 kilohertz set up, and I like to parameterize these values, such as our switching frequency. That way I can make one change and basically either change the frequency here in this parameter statement and the duty cycle, and then everything will automatically be calculated and populated. So here I show our pulse generator, and our time on is the duty cycle times the switching period, and the switching period is calculated from the switching frequency. And again, that's parameterized in our pulse generator for that voltage statement. One of the other things to note here is our gate to source for silicon carbide is a little bit different for this device than a normal power MOSFET or a normal silicon MOSFET. And our gate to source is -4 volts to 15 volts. So as you're designing with silicon carbide devices, you have to be in tune with the requirements for driving that gate to source on the silicon carbide device. And let me pull up the datasheet for the devices for this. Well, let's do a quick calculation. With a duty cycle of 0.75 and a bus voltage of 400 volts, we should see an average voltage across this load of about 300 volts. And therefore, we should see 300 divided by 20, our resistance. We should see about a 15 amp current on the average source current through our load, our series load right here. Now let's quick go over to the data sheets, and I just want to look at, here's the data sheet for the MOSFET that we're going to work with. The part number is C3M0045065K, and you'll notice on the data sheet it has what's called a Kelvin pin. And if some of you have worked with sense resistors, they'll have 4 pins. 2 of them are called Kelvin pins, which you'll measure the voltage off of, oftentimes with an operational amplifier. And then the other 2 pins on that sense resistor, the 4-terminal sense resistor, are for where the major current draw is through the sense resistor. So here, as you see, our major draw of current is going to go from drain to the power source, which is pin 2. But we will apply the gate to source driver voltage on pin 3 and 4. And so here we see pin 3 and 4 is where we'll put our gate to source. So they call that a Kelvin pin. However, the current is going from pin 1 through the switch and out pin 2. So again, our gate to source on pins 3 and 4. We are going to, for our flyback, because we have an inductive load, we want to put a flyback diode in there, and we are going to use this diode, which I pre-selected. And notice it's actually 2 diodes that we are going to use in parallel. And we have the anode for diode 1 on pin 1, the anode for diode 2 on pin 3, and the case and pin 2 are connected as well. So we'll be utilizing this device in our... Now that we have the files copied into the symbol folder and the library folder, we can come back to our LTspice file. And one of the things you may have to do is save the file and then reopen it for LTspice to actually find those folders. And I have done that already. Now let me come up to our component, and I'm going to select our component. And here you see we have the Silicon Carbide Wolfspeed devices, and its folder is right there. So I'm going to navigate into that folder, and there are all of the different diode symbols that came with it. But I want the TO-247-4 lead, which is the package for the device we're going to use for this simulation. So I'm going to hit OK. And there's our device. And I'm going to put that in place. So notice again, we have our Kelvin lead and our gate. And let me connect our gate to source pulse generator, or driver if you will, to our gate to source. And there we have that all set up. And I'm going to leave that floating. You don't necessarily want to ground that. And notice it has 2 extra pins on here, TJ and TC. That is for the junction temperature and the case temperature. The models from Wolfspeed allow you to also do thermal analysis. Now, we're not going to do that. And if you read the documentation, it says we can leave these pins floating. So we're just going to leave those floating. But if you wanted to do more thermal analysis with the device, you certainly could. And there's some good examples on how to do that. But we'll leave those pins floating. Now, I have to now link this device to the model that we're going to use. So the way I do that is I'm going to use a .lib statement, so .lib, and I'm going to put that right there. And you can use a .include as well. I prefer the .lib. There's some very subtle differences, but I feel this one's a little bit safer. Now, if I right mouse click that, we'll open up an editor window, and this is going to allow me to browse and find out which library we want to use for this circuit. So I'm going to browse, and here we are up here. And if we go into the all LTspice device models, which we have created, I'm going to navigate into the all Silicon Carbide MOSFET LTspice models. And as I said, the device that I'd like to use for this design is going to be a C3M00. So let's see if I can find that. C3M0045O65K. So there it is right there. And all I have to do now is select that and hit open. And hit OK. And that will populate. Let me resize that. It's a pretty long file structure name, but it has put that right there. And so that created the .lib include. And so now the last thing I can do, well, there's actually 2 more steps, is I want to open this, and I want to actually get the specific name. And here's the name, and I'm going to copy that. And some people know that if I drill into that as well, I can create the symbol as another way of doing this. But get back in there. I copied that name because I want to place that name. We don't want it to be called NMOS. We want that to be called by the actual device name. So I'm going to paste that right there. And that is the device name. So now we have that all set up. I also want to add a Schottky diode for our flyback. With an inductive load in a DC chopper, we always want to have that flyback diode in there. Otherwise, we are going to get some hefty voltage spikes as we switch. So let's go into our component, and we're still in there. And the diode I want to select on this one is a C3D 265D. So let's go look for that. That's C3D 265D, and there it is right there. I'm going to hit OK, and I'm going to rotate this and put it up there, and notice that. And let me connect this up. Again, we're going to have these diodes operating in parallel. And I have the anodes connected to the bottom. I want the cathode connected to our DC bus, and I'm also going to connect our case. And that's one of the things when you're actually doing the layout, is to look, is that case isolated or not isolated? And so you can buy packages with an isolated case. This case is not isolated, and that does matter when you're doing the final layout. Just like adding the lib file for the silicon carbide MOSFET, we're going to have to provide the library for this diode as well. So let me add a .lib statement here, and I'm going to do .lib, and I'll put that right above here, and right mouse click on that. We're going to browse. So if you right mouse click on that, we were in the SPICE model. Let me go up here. This is going to be in the Silicon Carbide Schottky file folder, and this was a C3D, so we're going to look for those C3D. And this is the Cree Power SPICE models. And all of the Cree are all under one library. So all I have to do is click that. So there's numerous sub-circuit statements in there for that. And hit OK. And we have that added now. So now we should be all set to go. Hopefully, if I click Run, this is going to work. And it does. Let me close that up. And let's take a look at this. It's still doing its analysis, and we are 11% done. I'll cut the video, and so we'll come back to when all 5 milliseconds are done. All right, that took probably a little bit over a minute to do the 5 millisecond transient analysis. So now we can look at the results. And the first thing I'd like to do is always look at the current through our load. And we can see that that current ramps up. And we predicted it to be about 15 amps. And sure enough, it's about 15 amps of load through that, of current through that load. Now let's take a look at the voltage across our Silicon Carbide MOSFET, and let me do that. And there you can see the switching there. And let's just zoom in here around 3 milliseconds, and you can see that we have a nice switching waveform. Has a little bit of a peak there, but all in all, it models very well. And you can see there's some turn on time, and there's some turn off time, because we know we can't turn on and off instantaneously. So let's take a look at that, and we can look at the power. So I'm going to delete our voltage, and I'm going to delete our load trace. And let me, if you hover over the MOSFET and hit Alt, you'll get the thermometer to analyze power. So let me get the power. Let me zoom out, auto range the y-axis, zoom to fit, and there is the power trace. And We can zoom in here and get the power. And I got the transient out of there. One of the ways to estimate, or at least get an estimation of the average power, is once we have the power there and we can see the average power that's dissipated, is to hover over the title. If I hit Control and a left mouse click, it's going to bring up a waveform analyzer, and we see we have an average power that's going to be dissipated in our device of 41.26 watts, or 41.25 watt. Now you may think that's a lot of power. However, this device is basically 300 volts at 15 amps. So it is absorbing, our load is absorbing about 4.5 kilowatts. So 40 watts dissipated in this device is really not that much. We can zoom in further and look at how much switching loss, or estimate our switching loss, by looking at our turn on. So this one right here, this tall spike, is our turn on power, and then the shorter one is the model of our turn off. And let's zoom in there a little bit more. And you can see we are spiking up to about 7.2 kilowatts on turning on, and then we have a spike at about 3.2. And then right through here in the middle is going to be our conduction loss. So first let's look at what our turn on time is. If I put a mouse cursor over right about here and stretch it out and look down in the lower, and it might not show up on this video, but if you look down in the lower left, it's going to give us the delta, and it's about 44.4 nanoseconds for our turn on time in the model. And our turn off time in the model is going to be about 24 nanoseconds. So we have 44 nanoseconds and 24 nanoseconds for our turn on and turn off time. And we can estimate based on that our switching loss. So our switching loss is going to be 1/2, and we treat these as triangles. So 1/2 times that turn on time times this 7.2 plus 1/2 times this turn off time times this value. So again, we can get that switching loss. The conduction loss is the power that's dissipated while the device is on. So if we zoom in here during conduction, we can see that loss, and we're going to have to zoom in pretty tight. Now I'll do an auto range on the y-axis, and you'll notice we are at about 11.8 watts of conduction loss. So 11.8. And let's come back to our data sheet. If we look at our data sheet, the drain to source resistance, this had a drain to source resistance of about 45 milliohms. And so 0.045 times the current squared. Our current is estimated at about 15 amps, and we end up getting about 10 watts. So it's a little bit higher than what the data sheet would specify. So maybe our RDS might be modeled a little bit higher than 45 milliohms, might be closer to when you look at the data sheet. I think they say it can go up to 60 milliohms as well on the data sheet. And let's see if we can find that. Notice that the gate to source, in here again, silicon carbide, we're going to have to look at how we utilize our gate to source. But the gate to source recommended turn off voltage is -4 volts, and the turn on is 15. And that's why I had my pulse generator set for -4 to +15. That wraps up how to model a vendor device model in LTspice. We utilize the Wolfspeed Cree Silicon Carbide MOSFET and a Silicon Carbide Schottky diode for a DC chopper. And one of the things we looked at was the utilization of that Kelvin terminal, which you're going to see more and more on these high-power devices. We compared our simulation results to the datasheet, or a few parameters on the datasheet, and it modeled very well. I really like the tools that Wolfspeed provides to designers. Utilize those tools and have fun in your circuit simulation. Thanks for watching, and we'll see you later.